Impedance transformation and parameter relations. In this video, I'm going to cover what I think is the most important topic in transmission lines, and that is the concept of input impedance. After that, we'll discuss various relations of parameters. My derivations will weaken here. In the interest of time, I'm just going to show how a lot of these different parameters are related. Then we'll summarize everything in terms of special cases of terminated transmission lines. What happens if we hook a transmission line up to a short circuit, open circuit, and we match the line? We make the load impedance equal to the characteristic impedance. Input impedance. Sorry, this is a busy slide. Let's think about what's going on here. In the top, we have a picture of a generator. It's pumping out some signal. There's an input impedance Z sub G, the G for generator. And we put a dashed line here, and the Z in, the generator sees some impedance looking forward. That is somehow some kind of mix of the transmission line and load impedance or whatever else might be happening here. That's what we want to talk about. So the generator outputs a signal. It passes through this transmission line, and it reaches a load that we write as a load impedance. And our transmission line we're characterizing in terms of a complex propagation constant and its characteristic impedance. So the whole discussion we want to have, if we back away from this load by a distance of L, what is the input impedance that our generator sees? And it turns out it's not necessarily the characteristic impedance, it's not necessarily the load impedance, it's sort of a mix of these. And that's called impedance transformation. Let's look at this and derive some equations. Another busy slide, and this is not the derivation of impedance transformation, but this is a good way to visualize it. And what we see on the right, we have a load impedance, and we've listed what that load impedance is down here. So we have a complex impedance. So at this plane, looking forward, we would expect the input impedance to look like ZL. From that point, we're walking backward, and we can see the transmission line getting longer and longer and longer. And wherever we happen to be along this, here I'm showing what the input impedance looks like. And this number here is how far behind the load we are in terms of wavelength lambda. And in this case, that lambda is the wavelength on the line, not the free space wavelength. So I didn't include that sub-naught, sub-zero subscript. So we're always showing what the input impedance is looking from here forward. Now, if we watch the numbers, we'll notice certain things. At the red planes, we're always seeing the load impedance, and that makes sense exactly at the load impedance. But if we back away a half wavelength, we see our load impedance again. And we back away a half wavelength, we see our load impedance again. Looking in, every half wavelength, our input impedance repeats. So that's shown here, our input impedance for any integer multiple of lambda over 2, and this argument is the distance behind the load, how far we've backed away from the load, will always equal the load impedance. Now the blue lines here, when we back away a quarter wavelength, it turns out the impedance inverts. And our input impedance is not 1 over ZL. It turns out it's the characteristic impedance squared divided by ZL. But there is a 1 over ZL here, so inductors suddenly look like capacitors, capacitors look like inductors, and we'll see short circuits look like open circuits look like short circuits. Everything sort of gets backwards here at these blue planes. That is a quarter wavelength behind this plane immediately at the load. And of course, every half wavelength, we still see that inverted impedance. So every quarter wavelength it inverts. Here we see the load impedance. Here we see Z naught squared over the load impedance. Back up another quarter wavelength, we're back to the load impedance. Back up another quarter wavelength, we're at Z naught squared over the load impedance. This green line you're seeing here is just an illustration of the wave, so you can get an idea of the wavelength along the transmission line. So this impedance inversion we're writing this way. Our input impedance, a quarter wavelength behind the load, plus an integer multiple of half wavelengths, is always the inverted impedance, Z0 squared over ZL. Let's derive an equation to calculate the input impedance when we've backed off from the load by some distance. We start with the definition of the reflection coefficient. We define the reflection coefficient as the reflected wave amplitude divided by the forward wave amplitude. So in this case, the numerators are backward wave, and in this we have the amplitude of the reflected wave times the exponential describing propagation of the backward wave divided by the amplitude of the applied wave times the negative exponential describing the forward wave. At this point, we recognize we have essentially the same exponential here. We can bring this negative exponential to the top and end up with an e to the 2 gamma z. Now, notice this is a function of z. This means the reflection coefficient is potentially a function of z and can change as we back up over the line. Now we would like to take a look at the impedance as a function of z. If the voltage and current are changing as we back up from the load, possibly the impedance is changing as a function of z. We can use the math and figure out if that's happening. So we have the voltage and current as a function of position on the line. We derived these previously, and we have our reflection coefficient at the load. So we can take these expressions for V and I and plug it into this equation to get the impedance as a function of Z. Now at this point, we recognize we have a V0 plus in the numerator and denominator. We can cross that off and end up here. Notice this final equation is not a function of voltage. This is what we were expecting. The impedance of a line should not be a function of voltage. If it was, then something nonlinear is happening here, and we're only doing linear stuff. So the fact that the voltage does not appear in that equation and the current does not appear in that equation is a good sign that we have a correct answer. Now let's manipulate this equation. As a test to see if we're right, another test, the first test being the voltage and current doesn't appear there, let's set the distance equal to 0. That means we're butted right up against the load, and the input impedance should be the load impedance. So right up against the load, z equals 0, and our exponentials just go to 1. So we can cross those off, and we end up at a slightly different form. At this point, let's replace our reflection coefficient with our equation for reflection at the load. Now we multiply the numerator and denominator by this ZL plus Z0, and that way we don't have fractions in the numerator and denominator, and we end up here. At this point, we see in the numerator we have a Z0 minus a Z0, so we can cancel that. And in the denominator, we have a ZL minus a ZL. So we can cancel those and collect the other terms, and we end up with something much simpler. And now these 2's cancel and the Z0's cancel, and our input impedance sitting at the load is the load impedance. That's what we're expecting to see. So we've tested this answer a variety of different ways. Voltage doesn't appear in it, current doesn't appear in it, and the input impedance sitting at the load is the load impedance. So now we can go on with greater confidence. Now let's look at the impedance at some distance L. So we're backing away from the load a distance L. That makes the position negative L. So we go to our equation, and everywhere there was a Z, we're plugging in a negative L. So we can simplify that a little bit, get rid of the parentheses in that equation. Before we move on, I just want to note about this sign because this is very confusing. We're defining the load to exist at Z equals 0. As we back away from the load to the left, our position in Z is negative. However, this L is the distance backward that we go, so L is positive. And the way we reconcile that is Z equals minus L. So our actual physical position Z is a negative number. how far we've backed away from the load stays a positive number. And we're formulating our equation with L in it instead of Z. So the number when we use this equation will be a positive number that we plug in there. Important thing to remember when we get to solving problems. Okay, so here's where we were from the last slide. Let's remember our reflection coefficient was the difference in impedances divided by the sum of impedances. Let's put this expression into our input impedance equation. So we drop that in. We can multiply the numerator and denominator by ZL plus Z naught. And we can simplify a little bit, and here's where we end up. Now at this point, we have two exponentials where one is a negative, one's a positive in the exponent with a positive sign here, and a very similar thing with the negative sign. And if we look at this long enough, we might remember these are our definitions of the hyperbolic trig functions. Specifically, the ones with the positive sign, that's our cosh function, the hyperbolic cosine. Now, the sum of these two exponentials is actually 2 times cosh. Cosh is the exponentials divided by 2, so when we replace this, we'll have to remember to bring the 2 over here, and there'll be a 2 hyperbolic cosine. Now, our expressions with the negative sign in here, that's our hyperbolic sine function. And again, we'll have to remember to actually put in 2 hyperbolic sine in there. So when we do all that, now here is where we end up. To simplify further, let's remember the definition of hyperbolic tangent. It's the hyperbolic sine divided by the hyperbolic cosine. Now here's our equation from the previous slide. These 2's will cancel. Then what we can do is divide numerator and denominator by the hyperbolic cosine. So hyperbolic cosine will disappear from here and here. But in these two terms, we'll have the hyperbolic sine divided by hyperbolic cosine, which is the hyperbolic tangent. So dividing numerator and denominator by the hyperbolic cosine gives us that. And now we can replace the sine or the sinh over cosh with the hyperbolic tangent function. And that is our final equation for impedance transformation, backing away from the load. And we're putting a negative L in here just to remind us that this is actually physically a negative Z, but when we plug in L here, we're putting a positive number in there. Now let's think about how this would simplify if we had a lossless line. That previous equation was the general one. Well, for a lossless line, our alpha is 0. That makes our complex propagation constant, which is defined as alpha plus j beta, it is now just j beta. So we go into our previous equation, and everywhere there's a gamma, we put in j beta. Well, a hyperbolic tangent of a complex number actually reduces to an ordinary tangent. So the definition is hyperbolic tangent of jz equals j times the ordinary tangent at z. So that converts our input impedance equation to this for lossless lines. It stays the hyperbolic tangent with the complex propagation constant in it when we have loss in our transmission line. Now we can have loss in the load, that's no problem. It's just for lossless lines we get to use an ordinary tangent function instead of the hyperbolic tangent function. Now we're in a position, now that we have this ordinary tangent, we're in a position to look at how the input impedance repeats as we back away from the load. And we already saw that in the animation up front, that we back up every half wavelength, the input impedance will repeat. And that's really because we have this trig function at work here. That tangent function will give us the same number if we take an integer multiple of pi and add or subtract it to this beta L term. So our definition of beta is 2 pi over wavelength, if you recall. So we can use this definition to write this as an effect on length. So anytime our length changes plus or minus a half wavelength, our input impedance repeats. So every time we back away from the load, every half wavelength, everything repeats. And I'll remind you again, the wavelength here is the wavelength in the line, which is probably shorter than the free space wavelength, so that is not the free space wavelength. Now, just to foreshadow something coming up, when we start talking about Smith charts, it really makes this impedance transformation suddenly make a lot of sense, because right now it's kind of crazy. We have this load impedance, we're backing away, the input impedance is changing all around, doing all these crazy things, and we wonder, over what set of impedance values are we scanning? Yes, it repeats, and it's very difficult to visualize, and in fact, right now, it is impossible to visualize. When we get to Smith charts, it's a really neat way of visualizing impedance transformation, because we're just walking circles around this weird representation of complex numbers, and we can visualize the exact set of complex numbers that we'll get as we back away from a load. So that's a really neat thing. Let's work an example now. So here's our setup. We have a 50 ohm line. We're not specifying loss, so we can just assume that it is a lossless line. We're connecting that to a 10 nanofarad capacitor, so that's our load. And we're also saying the line has a phase constant of 60 inverse meters. It's a 1-inch section of line backed away from the load, and we're asking at 4 gigahertz, what does that input impedance look like? And then really, what is the effective circuit that the generator would see looking in at this input plane? And it may not be a capacitor that it looks like. So let's go ahead and solve this. So we immediately write our impedance transformation equation. We need to think about what all these different variables are. There's a lot of variables in this equation, and I'll warn you, this is an equation where it's rather easy to make mistakes. So Z0, this is the characteristic impedance of the line. This was given to be 50 ohms, so that's what we use. This beta times L, we were given beta was 60 inverse meters, and we were given L, that's 1 inch. Now we can't just multiply 60 by 1 because we have this unit problem here. Meters and inches are not compatible, so we have to change our units. So first thing we can do is convert inches to centimeters. And so we multiply it by this ratio that equals 2.54 centimeters divided by 1 inch. These are equal lengths, so this is equal to 1. However, the units of inches will cancel, and we'll get units of centimeters. The next thing we'll do is convert centimeters to meters. So again, we multiply by 1. These are equal lengths, 1 meter over 100 centimeters. That makes the centimeter units cancel, and we're left with meters. So we multiply all that out, and we get 1.524. Now on to ZL. This is our load impedance. All we were given was the capacitance. That's not yet an impedance. Impedance is 1 over j omega times capacitance. Well, we were given frequency, so let's write our angular frequency in terms of ordinary frequency. So we put in a 2 pi f here. Now we can plug in our numbers. J 2 pi. This is our ordinary frequency, 4 gigahertz. And our capacitor, 10 nanofarads. So our impedance comes out being negative J 0.004 ohms. Load impedance. Wow. Okay. Now we plug all these numbers into our input impedance equation, and out comes this number. This is the input impedance after that 1 inch of line. Essentially, J1 times 10 to the third ohms. We're not done yet. We have to think about what that actually looks like to a generator driving this 1 inch transmission line hooked up to the capacitor. Well, it's purely imaginary and positive. That is an inductance. So to figure out what value inductor it is, we relate our input impedance to the inductance. So the input impedance is j omega, whatever this equivalent inductance happens to be. So we can solve this equation now for the equivalent inductance. And we just see that it'll be the input impedance divided by j omega. Well, we'll put it in terms of the ordinary frequency again. So input impedance over J 2 pi F. Now we have all the numbers we can throw in here. We just calculated our input impedance, so we can throw that in. And we know our frequency, 4 gigahertz. We turn the crank, we get 4.2 times 10 to the minus 8 henries, which is 42 nanohenries. So if we hook the generator up to that 1-inch line, which is then hooked to the capacitor, as far as the generator knows, it's driving a 42 nanohenry inductor. And it can't know any different. It acts just like that. There is no way to tell the difference. We could literally take that generator, hook it to a 42 nanohenry inductor, and then have a second circuit where it has the transmission line and the capacitor, and the generator can't tell the difference. So we made a capacitor look like an inductor. I think that's kind of interesting. Now we'll talk about some parameter relations. And in the interest of time and to avoid confusion, I'm not going to derive these. They're rather simple derivations, and based on everything we've done, you should be able to perform these types of derivations. It's also in the textbook. I'm just going to spit it out and talk about it for a bit. So maximum, minimum voltage and current. In terms of the voltage standing wave ratio, of course, these things are very tightly related. That's how we define the voltage standing wave ratio. So the minimum and maximum voltages, remember, we derived this from our expressions of the waves on the line. Well, we can also calculate these from the VisWAR. So the VisWAR can tell us what the maximum and minimum voltages are. And really, essentially the same equations to calculate minimum and maximum currents. Be careful, there's some minor differences here. For example, we don't have a Z0 up here. We do have a Z0 down here when we're calculating currents. Well, we can put our characteristic impedance in terms of VisWAR. So it turns out our characteristic impedance, if we know the maximum voltage and the maximum current, the ratio of those is the characteristic impedance of our line. So here's actually a clever way we can measure characteristic impedance, because we can drag a probe along the line and figure out what the maximum and minimum voltages and currents are. Likewise, we could look at the minimum voltage and minimum current, and those ratios will also give us Z0. Well, now we have expressions for Vmax, Vmin, Imax, Imin, and we can put the characteristic impedance in terms of VisWAR. So when we do that, we get some pretty simple equations. And we can also calculate, if we're driving a load and we're backing away from it and we see this input impedance go up and down, we can calculate the extreme values too. So the maximum input impedance our generator would see is Z0 times VisWAR. The minimum input impedance is Z0 divided by VisWAR. And so we can limit the input impedance that our generator would see. And so if you're designing a system and putting it together, this is something you would look at to make sure that your generator is able to drive those impedances, and those impedances maybe aren't outside the specifications of your generator. Let's work an example to bring all this together. Let's say we have a 50 ohm line connected to an antenna with a 72 ohm impedance. That seems rather mismatched. And we have a signal that's 24 volts peak to peak. One question could be, what is the reflection coefficient at the antenna? We have a 50 ohm line hooked to a 72 ohm antenna. So our reflection coefficient is just the difference in impedances divided by the sum. We plug in our numbers. The antenna now is the load impedance. And of course, the 50 ohms is our characteristic impedance. And we get 0.18. Now we could ask the question, what fraction of the input power is delivered to the antenna? We know now that some of that power will get reflected. How much is actually making it to the antenna? So one thing we can do is calculate the fraction of power reflected. That's the magnitude of the reflection coefficient squared. And if we work that, it's 0.03. But the power that gets to the antenna is the transmittance. And we can get that very easily. The transmittance is just 1 minus R, or 0.9, and on the percent scale, 96.7%. So it turns out, even though we have this, what seems like a pretty big mismatch in impedance, 97% of the power is still making it to the antenna. Many people will believe this is not even a problem. Okay, what's the VISWAR on the line feeding the antenna? Well, we know our reflection coefficient, so we look to our equation for calculating VISWAR given reflection coefficient, plug in our numbers, and we get 1.44. We can also express VISWAR in dB, and we get about a 3 dB VISWAR. That's considered a relatively low VISWAR. Next question, what is the minimum and maximum voltage on the line? We know this won't necessarily be exactly our driving voltage because we have a standing wave that can make that bigger and smaller than our driving voltage. So first of all, we need to convert from peak to amplitude. So the amplitude of our applied wave is the peak to peak over 2. So the peak to peak means the very minimum voltage of our generator, which goes negative all the way up to the positive voltage. The amplitude is just from 0 to the peak. So it's our peak to peak divided by 2. So 24 volts was our peak to peak. That means our actual amplitude of the applied wave is 12 volts. Now we can calculate the minimum and maximum voltage that will be on the line in the presence of that standing wave. Here's our equations for doing that, and we throw in our numbers, and we see that the minimum voltage that our line will see is 9.8 volts, and the maximum is 14 volts. Now, while it is not a problem here, we will always do this calculation and figure out what is the maximum voltage that will be on the line. Because if we have a high voltage system, it's that maximum voltage that could break down your cable. So we'll always calculate the maximum voltage and make sure that the system can survive it. We probably don't necessarily need to look at the minimum voltage, but definitely the maximum voltage. If that's exceeded, we're probably going to get arcing. Now we can calculate minimum and maximum current on the line. So we grab our equations for doing that. We can calculate it from the minimum and maximum voltages and the impedance. That's very easy to do. And we get a minimum current of 0.19 amps and a maximum current of 0.28 amps. And again, while this is not a problem here, we will always want to check our maximum current, because if we're transmitting high power through this line, that maximum current will create heat. And we need to make sure that our system can handle that heat. So we're checking the maximum voltage for arcing and breakdown. We're checking the maximum current for heating problems. So what's the total range of input impedances that a source could see? That's our minimum and maximum input impedances that we get from the minimum and maximum currents. And it turns out the minimum input impedance that we will see on this line is 34 ohms. Maybe I should say 35 ohms. And then the maximum is 72 ohms. That puts our input impedance in this range. And so when we're buying our generator or high power amplifier or whatever it is driving this antenna, we need to make sure that that can handle load impedances in that range. If that drifts outside the range of what our amplifier or driving circuit could handle, we're going to have problems. Let's end this with a quick summary of different special cases of terminated transmission lines. The first is the shorted line. This is where the load impedance equals 0. In this case, the reflection coefficient will be -1. And why -1? Well, if we have a short circuit, the voltage has to be 0. And so the only way for the voltage to be 0 in the presence of the applied wave is if the reflected wave is 180-degree phase shifted. And it's a shorted line, so 100% has to reflect. So the 100% reflection gives us the 1, and the fact that the voltage has to be 0 at the line means we need a negative number here. So the reflection from a short circuit, reflection coefficient, is -1. The voltage standing wave ratio is actually infinite. That's because we get 100% reflection, and that reflected wave is able to cancel the applied wave and get the standing wave down to exactly 0. That allows our viswar to approach infinity. That does not mean the amplitude of the reflected wave is infinite. That just means the standing wave goes all the way down to 0 because the reflected wave can perfectly cancel the applied wave. Minimum and maximum voltage on the line. Since the standing wave goes all the way down to 0, the minimum voltage is 0. Since the reflected wave has the same amplitude as the applied wave, the maximum voltage is when they add together, so it's 2 times the amplitude. Minimum and maximum current. Again, the standing wave goes to 0, so the minimum current is 0, and the maximum current is twice the maximum current of just one of the waves, which is the amplitude divided by impedance. The input impedance. Well, we really have 2 cases here. If we have a lossy transmission line hooked to a short circuit, or we have a lossless line hooked to a short circuit. And they look very similar, just one involves a hyperbolic tangent for the lossy case, the general case, and then we have an ordinary tangent for the lossless case. And the ordinary tangent approach tends to be how we think about things. So what this tells us, for the lossless line, the input impedance is purely imaginary. So it's purely reactive, no dissipation, no loss happens in the line. We'll also see that if we're driving a capacitor as the load, that it alternates between inductor capacitor as we're backing away from the load. And last, the range of input impedances that we could see. Well, at the point where the voltage and current go to 0, that really looks like a short circuit. So that's our minimum. And then we have points where the voltage and current have their full swing, and that looks like an open circuit. So our input impedances can go from short to open. Something else sort of neat, if we terminate our line with an open circuit and measure the input impedance, we'll call that Z in open, then we short circuit our line and measure the input impedance. If we multiply these 2 things together, we actually get our characteristic impedance squared. And this is a really clever way to measure the characteristic impedance. So we short the line and measure the input impedance, open the line, measure the impedance, multiply those 2 together, take the square root. Neat way to measure. Now we'll look at an open circuit line. And what we're going to see is the conclusions are almost exactly the same, just some subtle differences here. And that's because we still get 100% reflection from an open circuit line. One distance already is that we have a positive sign on the reflection coefficient. We still have a 1, so we're still getting 100% reflection. It's just that there is no 180-degree phase shift of that reflected wave. Viswar, because we get 100% reflection, the reflected wave is able to cancel the applied wave. We still have an infinite viswar. Minimum and maximum voltages are unchanged because we have this infinite viswar. Minimum and maximum currents are unchanged, again due to this infinite viswar. The input impedance, almost the same as we had before, but instead of a hyperbolic tangent, we actually have a hyperbolic cotangent and then an ordinary cotangent. Otherwise, the story stays the same. If we're driving a capacitor, as we back up, it'll look like an inductor, then a capacitor again, then an inductor again, as we're backing up. And the range of input impedances that we scan through goes all the way from a short circuit to an open circuit. Now let's say we have a matched line. So that means the load impedance is equal to the characteristic impedance. So if we have a 50 ohm transmission line, we're asking the question, what if we hook it up to a 50 ohm load? Well, if these are matched, the reflection coefficient goes to 0. That means there will be no reflected wave. If we're trying to get power to a load, this is ideal. This is what we want. The voltage standing wave ratio is 1. That's the minimum value that viswar can be. And that's because the maximum voltage and minimum voltage are equal now. And why is that? There is no reflected wave. We just have this uniform forward wave that's not changing voltage. So the minimum and the maximum are the same. Okay, so we just said this. Minimum and maximum voltage are the same. They're just the amplitude of the applied wave, and that applied wave is just traveling along, not decaying or growing, just staying nice and uniform. Same story for the current. The minimum and maximum currents are the same. The input impedance always looks like the characteristic impedance. Or we could also say the input impedance always looks like the load impedance since they're equal here. So as we back away, the input impedance is not changing, so the generator really doesn't see anything different. And this is a telltale sign if we have a mismatch between our line and the load, as if we cut our cable, we make it shorter or longer, and properties of the system are changing. That's a surefire sign that there's a mismatch somewhere in the system, because when things are matched, cable length doesn't matter. Our minimum and maximum input impedances, well, the input impedance doesn't change, so it will stay fixed to Z0 or ZL.